Building a real-time conversational AI means operating inside a strict 800-millisecond response loop. If the system takes any longer to process speech and return audio, the illusion of human conversation breaks down. At this scale, the choice of interface dictates the system's physical topology. This structural contract defines exactly where a system stores its state, how horizontal scaling occurs, and how tightly different backend components couple to one another. Our target architecture is a real-time conversational AI platform. It begins as a black box, isolating internal operations. Splitting it open reveals three boundaries: the public gateway for external traffic, the internal core for heavy compute, and the partner ecosystem for third-party models. Solving the latency constraint across these boundaries requires a polyglot interface approach. We must match the specific protocol to the physical constraints of the data it carries. We start at the public boundary. This zoomed-in node is the /gateway, the point where external client traffic first hits our system. Because conversational AI has conflicting demands, this incoming stream bifurcates into two distinct paths: the control plane and the data plane. The control plane handles session allocation, user authentication, and system configuration. To govern this administrative traffic, we implement a REST, or Representational State Transfer, interface. The core architectural constraint of the REST paradigm is statelessness. Statelessness mandates that the server retains no session information or history about the client between requests. Every incoming action is processed in isolation, and the server wipes its context the moment a response is sent. Stripping servers of local state allows trivial horizontal scaling. Any backend instance can process any incoming request. Because of this isolation, gateway instances sit behind generic Layer 7 load balancers. As traffic spikes, we simply spin up identical stateless nodes to spread the load. The constraints change in the data plane, where the system is actively ingesting continuous, real-time audio frames from the user. REST fails for this ingestion. Opening and closing HTTP handshakes for every few milliseconds of audio creates overhead that violates the 800-millisecond budget. The architectural solution for media ingestion is a stateful WebSocket API. This establishes a single continuous pipe that streams frames bidirectionally with minimal packet overhead. The gateway relies on a dichotomy. REST forces clean boundaries to scale control logic, while WebSockets allow for an uninterrupted real-time data flow. Moving inward, we hit the internal core. This specific hop connects the /orchestrator to the /STT streamer. This is a backend bottleneck. The system must transfer massive amounts of continuous text-to-speech data between the stateful orchestrator and backend worker pools. Passing traditional, bulky REST JSON payloads here would choke the compute hop. The serialization cost of converting heavy text files back and forth would destroy the latency budget. We require a protocol optimized for high throughput, machine-to-machine communication, remote procedure call, or RPC. The primary objective of RPC is achieving location transparency across a distributed network. Location transparency makes a remote network call function like a local method in the developer's code. The mechanism powering this is the IDL, or Interface Description Language file. The IDL serves as a language-agnostic contract. During compilation, it generates highly specific client and server stubs directly into the application code. These stubs serialize application data into efficient, tightly packed binary packets for transport. The payoff is that gRPC abstracts the network plumbing away entirely. Binary serialization allows structured data frames to bypass heavy text parsing, hitting the backend worker pools with raw efficiency. By skipping data translation, our single-threaded event loops stay focused on execution, ensuring they are never blocked by formatting tasks. Internal core communication demands RPC. The necessity for throughput outweighs the need for restful resource hierarchies. The final boundary involves making outbound calls to external partner APIs, specifically LLM inference engines. Distributed network calls carry an inherent risk known as the uncertainty problem. If a connection drops, the system cannot know if the remote server crashed before processing, if the packet was dropped in transit, or if the operation succeeded and only the acknowledgement vanished. External partner networks are inherently unreliable and enforce strict financially tied token rate limits for every interaction. To survive this net worth uncertainty, we implement a defensive architectural pillar, idempotent operations. Idempotency is the guarantee that performing a specific operation multiple times yields the same result as performing it only once. We wrap outbound API calls in unique tracking IDs. This acts as armor. If a packet is lost, the system safely retries. Even if multiple packets arrive, the ID ensures the action is processed only once. Without idempotent wrappers, automated retries over flaky networks would trigger double billing and drop conversational turns, breaking the 800 millisecond illusion. Pulling back, we can now view the fully assembled architectural map running in synchronization. The control plane relies on stateless rest to achieve horizontal scaling. The data plane utilizes stateful WebSockets to maintain uninterrupted media streams. The internal core uses gRPC to guarantee back-end compute throughput. A resilient distributed system survives by mapping specific interface paradigms to distinct operational constraints. The concept of a one-size-fits-all API design is a myth. With the topology set, the engineering execution begins. Is the next step to model the internal protobuf IDL specification, or to write the architecture decision record for our public WebSocket frames?